Hello, everybody. It's nice to see you here. My name is Andrei Kvapil. I will talk a little bit about myself first. I start my Kubernetes experience working at Vedas. It is biggest Czech hosting company. So I got a lot of experience automating deployment of 1,000 of servers and deploying storage, networking stuff, and also virtualization on top of this. Then I switched to work for Pelark. We were developing a Kubernetes platform, and since 2023, I started my own business providing automation solution for data centers and open source solution for ordering managed services. My today's presentation can be split to 4 different parts. First, I'm going to tell you about Kubernetes On-Prem challenge because it is not easy to install Kubernetes On-Prem, and I'll tell you how exactly it is. The first question, do you like using Kubernetes in cloud? I guess yes, because it is pretty easy. Old joke, there is no cloud, it's just someone else's computer. So today, when you're operating with Kubernetes on cloud, you're just operating with this layer of Kubernetes when you have APIs, when you have CSI volumes, networking, everything pre-configured and working for you. But if you are a service provider, you have to worry about this stuff. How you do virtualization, network isolation, how do you bootstrap your nodes, how do you update your system, provision Kubernetes kernels and kernel modules, and even do backups for etcd clusters. So today we are going to talk about this part. How can you build your own Kubernetes as a service on bare metal nodes? The typical scheme when you work with Kubernetes on cloud, you can see this scheme. So you're interacting with Kubernetes control plane, which is working independently, and you have separate services for load balancing, for storing the data, and you have workers which are fully ephemeral, and they're needed just to execute your workloads. Those nodes, those workers can be scaled down, scaled up. You can even remove all the workers, and your data will persist on existing persistent volumes. And when you create cluster again, create workers, your workload will be running, and load balancer will continue sending the data, the user requests to your workers, and they will continue consuming the persistent volumes. So this scheme works very well, but when we use Kubernetes on bare metal, we have something different. So let's talk about how can you make your own Kubernetes cloud. When we're talking about Kubernetes on bare metal, we usually talk about installing Kubernetes using kubespray or some similar method. For example, if you have bare metal nodes, you just install it there and you can use it as is. The problems here are that instead of this beautiful scheme, you got something like this. When you have nodes, you have control planes running on the same nodes, you have storage there, you have load balancers. Of course, you can move storage somewhere away, but still there are a lot of stateful services which are usually not prepared to be running this way. This scheme have no convenient management. The updates for it are really painful because you have to migrate the data somehow, switch replicas and things like that. It does not support autoscaling. You can't actually just autoscale bare metal nodes if you have no hundreds of the nodes. And there are no multi-tenancy. Actually, Kubernetes was never developed as multi-tenant solution, as OpenStack or CloudStack or some other cloud. When you're trying to solve those issues, you can find that you can use just private cloud like OpenStack. You can deploy your own OpenStack. In this way, we just use OpenStack on bare metal nodes and run multiple Kubernetes clusters on top of it. In this way, all of this working fine, but the problem is who is responsible for OpenStack? Because OpenStack is a very complex system. It consists of a lot of different microservices, databases, and they somehow interact with each other. So if you want to have OpenStack, you probably need separate team of the engineers who will support it. And option 3, run Kubernetes in Kubernetes. In this way, you can just replace OpenStack with Kubernetes. Nowadays, Kubernetes already have everything needed to run Kubernetes clusters inside and run other Kubernetes clusters just using infrastructure Kubernetes cluster. I will talk about this scheme, and we can put few terms like the infrastructure cluster we will call management cluster, which is used to run all the infrastructure services, and tenant clusters, which are actually user clusters. used to run user workload. The benefits of this scheme is that you always have the same ecosystem. You don't need to have specific tools for managing infrastructure cluster. You can use Helm and kubectl, actually normal tools for interacting with Kubernetes you can use to configure your infrastructure itself. It does support multi-tenancy because you don't let users get into management cluster. They have their own tenant clusters. And finally, you get the same scheme like you have in the cloud, where you have data separated, load balancer separated, and you can also enable after-scaling for the nodes, which are now just pure virtual machines. Management clusters still have the same approach, but we can limit it only to be responsible only for certain things, like running virtual machines, Kubernetes clusters, and databases. This way, we performed platform, so we made a solution. It is open source solution, which allows you to simply swap bare metal servers to have everything pre-configured to be able to run Kubernetes clusters, databases, virtual machines, and things like that, and have monitoring included as well. This is how it looks like. This is simple dashboard where you can just click and install what you want to. For example, Kubernetes cluster, click and install, and you have Kubernetes cluster. You want Rabbit, you want Postgres. Everything of this is already orchestrated and pre-configured to be usable. Every application actually just Helm chart, which consists set of YAMLs which are managed by operators. For example, if you deploy a virtual machine, you just need to simplify simple YAML file. So this is layer 1, and layer 1 should be responsible to have Linux distribution with all needed kernel modules, with kernel version, because it is really important to have other infrastructure components working like storage and networking. And it is also responsible for providing a Kubernetes cluster, and we use Talos Linux for it. Layer 2 is storage, networking, and virtualization. So we based it on technologies like LinStore, OVN, and KubeVirt. Then layer 3, it is ordinary operators, cluster API, and monitoring. And the layer 4, I would say application layer, where you can order managed Kubernetes clusters and databases. All of these are orchestrated by Flux CD. Let me show you how exactly it works. Let's talk about layer 1 at first, and I will explain you how we orchestrate Talos Linux. Let's say you have an infrastructure. It can be virtual machines. Those virtual machines can be cloud. It can be virtual machines on bare metal servers or bare metal servers itself. Talos Linux it is Kubernetes specific distribution, which already have ready-made images for every platform you can imagine. For example, previously we were using images for Proxmox and OpenStack. There are more generic ways to install it using ISO or Pixie booting. And you can also try it out in your local daemon. It's operating like kind, and you just run Talos cluster and it creates your local cluster, so you can try the same things on your local machine. To initial bootstrap, Talos suggests you using the next approach. So you're booting your virtual machines from Talos Linux image, and then you have to configure it. To configure it, you have just one configuration file. This is very cool. You can configure the whole machine with one configuration file. This configuration file split to two sections. The machine section, which describes the configuration for specific machine you have, and cluster section, which calls the configuration for Kubernetes cluster itself. For example, machine section includes such information as what type of the machine. Is it control plane or worker? It includes certificates, how can you access it, network settings, like interface which you should use for communicate between the nodes, and disk to install. While cluster section includes the endpoint for accessing Kubernetes API, as well as certificates for Kubernetes itself and configuration for specific Kubernetes components. If you want to configure a machine, you just use talosctl tool, which is pretty similar to kubectl apply. kubectl, and you use talosctl apply, and your machine gets configured. Very simple. So to bootstrap your cluster, you can use this approach, but in our case, if you want to bootstrap the whole cluster, you can generate secrets, secrets file, which will hold all the secrets for the cluster. And then you can use this configuration file to generate configuration for your cluster itself. You use talosctl gen config with secrets, and you got 3 more configuration files. It is talos config, control plane, and worker. Talos config is pretty similar to kubeconfig, so you can use it to access Talos API. And you have two configuration files which can be used for configuring your nodes. If you want to apply it, you do talosctl apply, and this file get applied to the machine and machine get configured. So you apply this file to the 3 machines, and then you use single command to bootstrap etcd cluster. So you say talosctl bootstrap, and now the Kubernetes cluster get automatically configured and ready to use. If you want to update the node, you can apply another configuration file which you updated, and the node will remove all the workload from the node itself. So the node will be drained, it will take a lease, then it will be drained, then disconnect itself from the cluster, update itself, and join back. So very useful and ready for running the rest things. If you want to access this cluster, Talos also has its own implementation for virtual IP. It is some kind of floating IP which can be moved automatically across the nodes. And when you're accessing the nodes, it will be always running on the node which is always accessible. Our approach is slightly different because we want to provide really simple interface for installation to our customers, but we want to use Talos Linux and all its advantages. So we introduced our own method, actually installer for Talos Linux for the nodes. It's called Talos Bootstrap. For example, if you have the few nodes, you can run few Docker containers, which calls temporary DHCP server and PXE server with our image. And then you use this tool to configure it. For example, the servers are booted, and then you use it to configure the first node, the second one, the third one. How does it work? How does it look inside? This is actually old school Debian installation principle, where you can just find all the nodes you have. You put host name, choose the disk, put network settings, click next. Finally, you get Talos Linux configuration file. You apply it, wait a while, and then you have ready Kubernetes cluster with our system. Inside of it, we already prepared the image with all the needed Talos modules. So we operating on bare metal, so we included all the needed firmwares and also modules like DRBD and ZFS for our storage. This is stable layer for building the rest things. Actually, those ones, let's talk a bit about them. The system components. How can you bootstrap your cluster with predefined stack of technologies? Every time when you're using Kubernetes, you have to install cert manager, some bug policies, CNI plugin, monitoring, and things like that. Actually, in this way, I can say that Talos Linux works well with FluxCD. So you can use FluxCD to deliver all of these components into the cluster. You can even specify it in extra manifest section for Talos config. So the first line will install FluxCD, the second one can apply configuration for your cluster. But we use a slightly different approach because we build a platform and we want to provide unified way for installing and configuring our components. So in our case, FluxCD doesn't go to Git repository and it just downloads the configuration from its own container. So we let user to apply configuration file to run container. This container holds Helm charts. It actually runs Helm charts repository, which contains all the needed Helm charts for our platform. And then it also installs FluxCD, and FluxCD installs everything from this container into the cluster. If we want to update to newer version of platform, we just update this container, which holds already all the needed configuration and Helm charts for which should be applied to the Kubernetes cluster. And FluxCD just applies the newer version of components. This way, we deliver the storage, the networking, which is also based on Cilium and KubeOVN. We deliver monitoring and KubeVirt itself. In this layer, we already have pre-configured system to run user-faced applications. And these are done the next approach. Let's talk about management Kubernetes first. We provide fully compatible Kubernetes like you have in cloud. It supports all the needed things like load balancers. You can order physical volumes. And then you can also use after scaling. This is done using Kamaji solution. Kamaji, it's more likely Kubernetes control plane operator. It actually provision you control plane, which is fully compatible to Kubernetes. So you can join any node, any Kubernetes join, any Kubernetes node can be joined to the Kamaji control plane. And the control plane actually running as a class, as pods. If you'll take a look on how Kubernetes is working, you can consider it as usual application, which has few components like microservices, API server, scheduler, controller manager, and database. So all what Kamaji do is just runs those components, using operator approach. Under the hood, we use Cluster API for provisioning those clusters. Cluster API itself has connections to multiple providers, but we use KubeVirt, so we run virtual machines right in the same cluster. For example, if you want to provision Kubernetes application in our platform, you just have to fill this small configuration file where you specify that you want these node groups with this amount of resources, and it will expand to multiple Kubernetes resources. This is actually Cluster API spec. So we have cluster resource, which linked to Kamaji control plane, which is managed by Kamaji control plane provider. We have KubeVirt cluster and KubeVirt machine template, which is managed by infrastructure provider. And we have Kubernetes config template, which is managed by Cluster API bootstrap provider. Actually, this Kubernetes config template used to, and we also have machine deployment resource. It's pretty similar to how Kubernetes deployment working. So if you have deployment, you have state, you have a replica set, and you have pods. Machine deployment expanded to machine set, which creates actually machine, which actually virtual machine in KubeVirt. And as about databases, we use ordinary operators. So we don't use pure Helm charts because they don't provide full lifecycle management. We use Helm charts just to pack a set of YAML files, but those resources still managed by operators. In this way, you can create databases, manage users, create database like logical database, and configure monitoring for the provisioned database itself. Those are a set of operators we use, but users don't interact with them directly. So they have covered API with those Helm values we provide to configure by user. So every application here, it is actually pure Helm chart, which holds 2 or 3 different YAML files, which are managed by operator. For example, if you order database, operator will take care of I almost lost my laptop. Database is provisioned by the YAMLs are templated and put into Kubernetes API, but it is still managed by operator approach. But the Helm charts are fine because you can also configure how they should look like for the user. For example, this simple YAML file can be expanded to 3 YAMLs like Redis failover service and VM service scrape, which is actually service scrape for Prometheus. We just use Victoria Metrics instead of Prometheus. And this way you can provision managed Kubernetes clusters, databases, virtual machines. So you can pack whatever you want to run in Kubernetes. You can just put it into simple Helm charts, and they will be managed like they will still have full life cycle management through the operators. And as about multi-tenancy, this is interesting topic. We still don't allow users to get access to management Kubernetes cluster. If they want to run their workload, they're forced to create tenant Kubernetes cluster. So we usually provide our system as backend for billing system, for existing billing system, or for existing portal of service provider where they can create services by just putting simple YAML files into management cluster. But if they run tenant Kubernetes cluster, all the components for this tenant Kubernetes cluster are also running outside. That means that user can request persistent volumes, services. They will be magically appeared in their cluster. but they will not see this interaction. So all the controllers are running outside. And also we have tenant model. When you're installing every application, you can also install additional tenant. This allows you to make additional tenants, and every tenant have its own domain assigned. For example, tenant root, like root user in Linux. You can also add additional users, and they will have the same naming like you queried. Inside of every tenant is actually a Kubernetes namespace with additional specific services. Every tenant can have separate etcd cluster for holding Kubernetes configuration file, separate monitoring stack, and separate ingress controller. Now we also have CVDFS for provisioning S3 buckets. It is also tenant-specific service. So if we have, by default, the upper tenants always have access to the bottom tenants, but bottom tenants can't have access to the upper tenants. And if you run some application inside of tenants, they automatically find which services they can use. For example, Kubernetes cluster here can use etcd from tenant foo and ingress from tenant green, because tenant foo have no separate ingress controller. The same way here, Kubernetes cluster here will use monitoring from tenant foo. This allows us to create this scheme when you can create one organizational tenant, which will hold one Grafana and one monitoring stack for collecting the metrics from all the Kubernetes clusters and services. And you can still have isolation between the namespaces if you create additional tenant for your users in this organization. So finally, we got all the environments which are unified and reproducible thanks to Talos Linux and Fluxcd. We made a simple interface for installation. You can try out it by yourself. The project is open source and available on GitHub. And our platform covers all the infrastructure stack. So we have storage, networking, everything you need actually to run managed services. It is easy to extend, so you can add just additional Helm charts. Almost finished. You can add additional Helm charts and system components. And we are open source, so just try it out. A few links. The link to our project, it is available on, it's called Cozystack. It is available on GitHub. Link to Talos Linux and Kamaji, which we use to provision Kubernetes clusters. Also, you might find useful this set of articles I wrote on blog.kubernetes.io, which explains how exactly the things working. So this is quick. All the approach is described in those set of articles. Thank you, Dario, who provided me slides about Kamaji, and Victoria, who drove this amazing presentation. Now I'm ready to answer your questions. Thank you.
Any questions?
That was very interesting. I've wanted to know a bit more about bare metal Kubernetes for a while. How does storage work?
We use Lean Store. I can find this slide. There are a lot of information about it. Lean Store, actually, it is not storage like Ceph. This is not clustered file system. It's more likely orchestrator. But you can imagine it like Kubernetes, but for block devices. It allows you to provision local volumes, and you can also enable replication, which use DRBD it's like RAID 1, which works on network layer. In our case, we use it for provision databases. Our databases are always deployed in clustered version. So we use data replication on database layer. We don't need to have storage-based replication. But we can't do exactly the same for user data because we actually don't know what they're storing there. For that reason, every persistent volume for the user, which is requested by user, we always enable replication. And this replication is done through the DRBD. Lean Store itself, very interesting solution. It allows you to enable encryption. You can use LVM, ZFS. The most important stuff that the data you store there, you can always access. Even if you get lost your metadata, if your control plane is not working at all, you can go directly to the node, use DD, and make a copy of your block device. And also it is very fast. If you compare it with Ceph, I think you will be surprised that it is not consuming so much CPU time. Just Google, you will find some presentation about Linstore. I guess it will be mine.